that we had a little change of schedule. Martin kindly agreed to come back and give us the second half of his talk during the next half an hour, and we'll start our panel at 4 o'clock then. So in order to get through the second half, we may sort of keep questions to bare necessities, like if you don't understand something and to get to the next slide, but then, the panel, there'll be plenty of opportunities for follow-up questions and larger issues and such, so thank you.
All right, thank you, and so thanks for again all the great discussion this morning about the classical capabilities and gaps as exemplified by DFT and coupled cluster theory. So now, what is a classical quantum chemist supposed to be doing in quantum computing research? And so basically, in my case, the answer is mostly collaborating with domain specialists, and this actually began back in 2005 when I had a very bright postdoc, Alain Asperger-Guzik, and a very bright student, Tony Dutoy, and we interacted with D-Wave and Peter Love, and then I left the area to Alain for a good 15 years or so. And then, thanks to my office neighbor, Birgitta Whaley, primarily, and also thanks to Lin Lin, I somewhat rejoined it more recently. And so I owe a great debt of thanks to Unpil from Birgitta's group, Wendy, our joint student, Hang from Birgitta's group, and James, Dip, Wendy again, because she's joint, Nicolay and Becca Toman from my group. So they're the people who define our quantum subgroup as a function of time. And we've been working on a few things that in the context of the success of classical quantum chemistry are really pilot experiments. So subspace diagonalization methods, so I'll talk to you a bit about the non-orthogonal quantum eigensolver, and then variational approaches. I'll talk to you a bit about unitary cluster gastro models, and then I will skip Wendy's work on near-term methods built on quantum phase estimation. There's not enough time. All right, so from a practical, classical, computational quantum chemist's point of view, the first question one should ask is, what is the key to viable quantum computing? And of course, the answers are well known. You need sufficient qubits, sufficient circuit depth, which is kind of code for error correction, and sufficient execution speed. And that's part one. And then you need a suitable problem, and that's part two. And so quantum chemistry enters as a possible domain specific answer to part two, and part one is largely out of our hands. We follow what is going on in the with the development of quantum hardware with great interest, but zero control or influence. And if you could do all that, then we can. Then notions like quantum utility become viable. And this is a cartoon taken from a nice article assessing the ARL, or the application readiness level, that sort of begins all the way from, the light bulb going off through to actually executing on a device. And the article more or less concluded that we were somewhere between ARL1 and ARL2 in most cases, as we ended 2023, and that was probably accurate. So that's that, and of course then quantum utility to me is can you do something useful on a quantum device that would not be readily done on a classical device, and we can certainly say what quantum utility is not, which is not solving a problem on a $10 million quantum device that could be solved on a $10,000 classical device. So we're really then looking for a peek into the future, and of course my group survives in some sense on, can we deliver computational software to chemists today? And so this is sort of for this reason a minority interest of mine, but it's important. And then the perspective is to go visit top500.org, which is a great website, because you can trace the history of high-performance classical computing from the early 1990s to the very present day. And so when I check checked it last night. The #1 supercomputer was El Capitan. That's out at Livermore at 1.8 exaflops, so 10 to the 18th adds and multiplies per second, and that is this data point right here. And then the number 500 system is interesting to look at because that sort of tells you a little bit about where the trailing vortex is. And then another thing that I looked into last night is, well, what's a commodity machine? So here's a Apple Mac Studio, the M4 Max chip. It comes in at the speed of the number 500, world's 500th fastest computer circa 2004 or so, 2004-5. So the point is that it took a long time. In my first talk, I had that quote from Mulliken right at the beginning. If you were here in the morning, you'll remember it. It took a while, 60 years of exponential growth, to actually fulfill Mulliken's prediction. And it's also worthwhile to just kind of think, Moore's law is kind of captured on this. But it's not a law, right? Moore's law is not a law. It's something that happened because a bunch of people were determined to make it happen. And quantum hardware is exactly the same. There's no law that says there will be exponential improvement in quantum hardware, but if there is adequate incentive and adequate excitement, then it could happen. And so what about a roadmap for quantum device progress then? So one amusing thing is that I think it's still true now, and it was definitely true when I first looked at this carefully about a year ago. Quantum volume is widely used to measure the performance of a quantum device.
I'm a bit nervous that we won't get to the quantum chemistry.
All right. Let's charge ahead then. But this is the basis for why should we do quantum chemistry. So I have to say it, which is that if you look at we have 4 years of exponential growth, and then this is what one vendor at least claims they will give us by the end of this year, by the end of 2027, by the end of 2029, and that will then be 7 years of exponential growth, which is enough to really take it seriously. It's an ambitious roadmap. Okay, so the chemistry. So let's first talk about strong correlation, which was what I think I and most people would agree is the most promising application. And so with Birgitte, I suggested that we explore a quantum analog of non-orthogonal configuration interaction, and Unpil and Dip and James and Oscar turned this into the non-orthogonal quantum eigensolver. What is this thing? It is to begin with a set of individually optimized determinants. These, in the simplest instance, would be solutions, stationary points of the Hartree-Fock energy functional, but it could be a density functional too. Because it's a nonlinear optimization, there are many possible solutions. If you can get a bunch of them, they will be an interesting basis, a set of n-particle basis functions, which in some cases, it's quite interesting, they are chemically obvious. So for instance, if you create a hole in this CrO4 2- on an oxygen atom, well, there are 4 spots to put the hole. So it's physically obvious that there are 4 natural n-particle basis states. That's 4 different sets of non-orthogonal orbitals, each of which is perfectly adapted to where that hole could be. And the result of that is if you interact those 4 non-orthogonal states together, you get an answer that you would need tens of thousands of configurations to get to if you used a single set of orthogonal orbitals. So in favorable cases, it is chemically obvious what the state should be. And in unfavorable cases, it's not obvious. So anyway, so that's that. And here's another example, which is if I take the lithium fluoride molecule, here's F- and Li+, so the last pair of electrons localized on F- at equilibrium, but as I pull it apart in the gas phase, that electron pair separates, and you get this competition between covalent and ionic character, and those can represent separate SCF solutions, and if you configuration interact them, you then get the ground state and an excited state, the ground state ionic at equilibrium, and the excited state covalent, and the opposite as you separate. So, so that's kind of the physical motivation. You can treat strongly correlated systems this way. The H4 system is with a square geometry is a case with an orbital degeneracy, and you can find 6 spin polarized unrestricted Hartree-Fock determinants that nicely describe H4. Yes?
Sorry, so to the uninitiated in chemistry, could you, including me, could you describe, could you say at a higher level what this means?
Well, let's see. The higher level, this is trying to echo this statement with 2 examples where it is obvious what the state should be if you know enough chemistry. So, so the point here is that chemists would say the fluorine atom is more electronegative than the lithium atom, so at equilibrium the bonding is ionic. But chemists also know that to strip an electron off an atom and give it to another atom costs energy. So, so at dissociation, the electron arrangement is different. The potential energy curve should then be some competition between those 2 limits, and then this is a compressed form of a correlated wave function for a very, very simple problem. So this is a case where we can identify what the non-orthogonal determinant should be, and that makes it a very natural way to proceed. And with just 2 determinants, you can do quite well. H4 then is something where imagine 4 separate hydrogen atoms. So each of them has 1 electron. These are just the arrangements of the spins then. And as you take them from infinitely far apart to interacting to make square H4, instead of independent spins where you pick 2 up, 2 down, the arrangement of which are down and which are up actually matters, and these begin to split apart, and the strong correlations arise in H4 from the interaction of those states together. So this is simply a very compact set of 4 electron basis functions to describe this 4 electron strongly correlated problem.
I have a question about the graph. Is your graph, are those experimentally determined, those curves, or are they theoretically?
These are everything in both my morning talk and this afternoon. There's not one experimental result anywhere, except insofar as these are numerical experiments. Yeah.
So operationally, what you're saying here is that you have this Hartree-Fock optimization procedure, which is very easy. And using chemical intuition, you can make good initial guesses for it, which then you run through a self-consistent Hartree-Fock thing to get your Slater determinant states.
Yep.
So then in this second example, for example, you know that there are 2 equally favorable chemical states. You initialize with what you think is the right thing. You run it self-consistently. While your initial guess may be orthogonal, they lose orthogonality as you run the optimization.
Right, so you finish up with, in this case, 1, 2, 3 different determinants that each have orbitals non-orthogonal to the other. And so what we're going to do now is then consider trying to do the strong correlation, exemplified by this, and weak correlations together. So the next thing we should do is dress these determinants with the effect of weak electron correlation, which in the cluster language from this morning would be the T2 operator. And at that point, you've got a theory of both the strong or static and the weak or dynamic correlation. And the interesting thing about this is that this is a theory that's exponentially difficult to evaluate on a classical computer because the matrix elements only terminate at n, the number of electrons. On the other hand, it is viable and in principle polynomial scaling on quantum devices. And so quantum advantage is something that, as we've seen in a variety of talks today, is tricky to find in general, but this is a specific example.
So what is the quantum algorithm?
The quantum algorithm here is, well, maybe on the next slide. And I don't have it all here. This is a hybrid quantum classical algorithm. The key quantum step is to compute the off-diagonal matrix elements here. And this is done with a Hadamard test. And so Classically, as came back to the previous question, you optimize a set of non-orthogonal reference states. You then get some dressings that reflect weak correlations, and then you evaluate the matrix elements in the small many-electron basis, and then return to the classical computer to solve a generalized eigenvalue problem. And so this is something we've then done for H4. The results are quite good in the sense that you can compare against full CI and look at the errors. And this is actively being worked on. So Wendy, who's sitting at the back there, is in the middle of developing a new software base aimed at direct testing of this algorithm on Quantinuum hardware. All right, so that's, yeah. Okay, all right, so then I want to...
Sorry, you're just using the quantum computer literally to compress the problem, is that right?
We're
Where it's
using
classically solvable. Have I understood this right?
No, that's not right. What's classically solvable is to take the undressed n-electron basis states and configuration interact them. So that's classically viable. What is not classically viable is to dress them with correlation and then work out the energy variationally. That's just as difficult as doing variational coupled cluster theory on a classical computer.
But, I mean, you had this quantum step and then you had this classical post-processing, which sound like you're extracting these, literally a matrix here, I and J,
That's
and then
correct.
you solve some classical problem on that.
Those matrix elements are exponentially difficult to work out on a classical device.
But somehow you're coming up with some classical sub-problem, and now you solve this,
We
right?
have, yeah, exactly. So we have identified what we believe to be a relevant subspace that includes the effects of strong correlation. We then, on a classical device, have a problem evaluating a matrix element of this form, because it only terminates at the
Okay,
number.
yeah. But this is what I meant, like you're compressing to some subspace, and now
That's
you can solve it
correct.
classically.
And in fact, one of the most interesting sort of open questions about strong correlation is how compressible is a strongly correlated wave function in general? And I don't certainly know the answer myself. Yeah.
I'm sorry, quickly, what's H hat?
This is the n-electron Hamiltonian.
Sorry, how does this, where does T come into all of this?
T is entering, well, we begin by constructing these T amplitudes, which are then written here as tau.
Ah,
So this is then a correlation factor, couple cluster style, but unitary in order to, so we translate from the non-unitary classical to the unitary for the quantum device. Yeah.
You just answered my question, so never mind.
Okay. All right, then I will actually skip this just to say that one of the questions is measurement efficiency, and Heng Ren has led an interesting study looking at classical shadows to do this. There's the original Hadamard-based approach, and then this classical shadow, and the classical shadow is favorable when you've got more states or seek higher precision is the result of that analysis. I will skip this in order to go on to, or maybe I won't.
good question. So, as far as you know, does that give an exponential speed up over classical? Or?
The NOQE is arguably an exponential speed up over classical. Like many of these arguments, it depends how you frame it. In other words, what is true to say is that the energy that comes out from a quantum simulation, from a quantum experiment, will be variational. To get the variational energy classically is exponentially difficult. So that's the quantum advantage, that if Brigitte were here in my place, she would be emphasizing even more strongly than I emphasize it. And maybe, since it is me, I should say that you could do this polynomially on a classical computer if you sacrifice the variational condition, right?
Which is the dressing? Is that what's the variational condition?
Well, that the energy be an upper bound to the true energy. So in other words, the same way I said this morning that coupled cluster theory on a classical computer is only sensible, i.e. polynomial effort, if you sacrifice the variational condition. So, so it is the quantum device that enables us to retain the variational property here that we couldn't retain classically without it being exponentially expensive. So that's the quantum advantage that lies in NOQE. Yeah.
So, you know, the number of problems where we have, you know, a well-defined problem with what we believe is an exponential speedup is like, you know, less than 5, right?
Come on.
So I think it might be worth like making this just 0.3,
Yep.
like isolating that and saying like this is a claimed exponential speedup. I don't know if there's a way to sort of strip away all of the other stuff and say like,
Well,
compute the inner products between these states. That is quantumly easy and classically hard. Like that would be a very already just super interesting, I think.
Yes. Yes, I agree, and yep. Yep.
But that is the claim.
That is indeed the claim. These classical sidestep, and again, it depends how you frame it. So classically, you can sidestep it, but you must give up the variational bound. So a concise way to say it is that a good electronic structure approximation should be variational above the true energy. It should also be size consistent, scale properly with molecular size. And those two virtues can be achieved this way. And so, you know, it's a little bit of a straw man, it must be said, but nonetheless, it is strictly true. So, all right. So then what else are we playing with? How do you do that dressing? How do you do that correlation factor dressing? One of the most interesting results is this unitary cluster gastro ansatz. This is, in principle, a re-expression of an exact wave function. If you carry the number of products here towards a large number. If you truncate it at a low number, you may then get a low complexity method that is actually quite useful. And so that is the unitary cluster gastro ansatz, where typically L is truncated. And yeah.
How's it unitary if there's only creation operators in the case?
Oh, that's a typo.
Thanks.
Okay, so yes, indeed, it is unitary there. Sorry about that. And indeed, K is anti-Hermitian. It has the character of orbital rotation. So if you have a destruction operator as the trailing one. Okay, so what do we do here? So Mario Motta and James Shi, who was then a postdoc in my group working with Birgitte's quantum subgroup, played around with a local or sparse model for the retained elements of the J tensor, and this is the local unitary cluster gastro model. IBM is actively using this for simulations, including one that was reported just 2 weeks ago or so on ground and excited states of methylene, and one that was reported last year on N2. The argument is that to some extent you capture the Hubbard physics that was discussed this morning, and secondly, you reduce quantum resource needs, and you may in fact even be able to map onto qubit connectivity, the device topology. And so as a function of L, that truncation, this is just showing that, that for the H4-like problem, which I think was actually 4-electron and 4-orbital cyclobutadiene, that as you go to a fairly low value of L, these methods become exact. And so that's interesting. And what we have been very recently doing, and this is work by Nikolay Tkachenko, who's a postdoc in my group, collaborating with Birgitte's group again, is exploring the best form of unitary cluster gastro, trying to get as much value as you can from L equals 1. And Same typo, I apologize. So copy. Nicolay considered three implementations. The first one is real antisymmetric parameters, and for K. The next one is pure imaginary, symmetric, and the third one is general complex. And so this implies a real, unitary, an imaginary, or a general. And applied to H2 dissociation, the results are quite interesting. The real unitary cluster gastro, which is what we used in the first version of NOQE, exhibits two local minima, actually. The imaginary one, we could only find one, and the error is much smaller. And for the 2-electron and 2-orbital problem, the general one turns out to be exact. So then scaling this up is pretty interesting. I'll skip that. The general one is clearly preferable, and what we are going to do next is try and use the general unitary cluster gastro with the NOQE for higher accuracy. And then I already showed you this morning, but to finish up and try and get the panel going, just want to say grand challenges, things we want to be able to do that we can't do. This oxygen evolving complex contained in photosystem 2 is a great example because it blends all of the difficulty of multi-scale modeling classically with strong correlation quantally. And so that's very, very interesting. And therefore, the kind of thing that we can think about trying to move towards simplified models of that core using the coming generation of 30 to 100 qubit error-corrected quantum devices. And as I briefly said at the end of this morning, I view this as a quantum embedding problem to be tackled by methods along the lines of density matrix embedding theory or cluster embedding theory that Avijit, who I see is sitting back there, has been working on. And the kind of vision that we put together talking with Avijit was this 3-level embedding where there should be some kind of feedback between a classically treated yet quantum mechanically modeled region and then the strongly correlated region that may be in the near future best treated on the quantum device. And then finally, this should also be coupled to large-scale motions of the outer protein, which is a problem in statistical mechanics. And doing some device analysis. This is Brigitta's group that's responsible for this. The estimation was that with the lowest levels of error correction, but not no error correction, we could perhaps approach this with on the order of 200 physical qubits and perhaps a manageable number of C0 gates. So all right, so let me try to summarize then. So this approaching era where we are now beyond the NISQ era and entering the era of logical qubits is exciting on the one hand, yet still not exceeding classical capability on the other hand. So we can assess quantum algorithms for their application readiness, and quantum chemistry is a nice area in the context of strong correlation. One thing to be aware of if you kind of bookend these quantum algorithms against the morning talk is that the algorithms we're talking about are not yet black box methods, and it would be highly desirable to have black box quantum algorithms. We talked a lot about the 5% this morning. I also want to note that strong correlations may well be less rare in excited states, and that oxygen evolving center is driven by a photon, by light. Black box in the sense that ideally you would just like to say, this is the name of my model, and now I will run it and get enough precision. So in principle, quantum phase estimation is a black box method, provided that state preparation is done properly and you control for precision. The non-orthogonal quantum eigensolver involves the unwanted addition of the n-particle basis states that have to be specified by the user. So that's not that's an example of a not black box method. let's see, the very interesting open question is around the exponential quantum advantage, and I have argued that NOQE for strong and weak correlations simultaneously is an example, and Birgitta and her student Oskar Leimkuhler have a very interesting archive preprint on complexity analysis on this. And on a personal note, it's unclear to me how compressible a strongly correlated wave function can be, and it is unclear to me whether or not classical strong correlation algorithms are actually mature or not. So there are interesting questions, and I think these connect nicely to the conclusions of the second talk of the morning. Hybrid quantum classical computing, I think, is essential, and of course, hybrid algorithms, the VQE and NOQE are already hybrid, but that notion is insufficient. We really definitely want to be pursuing the notion of coupling a QPU treatment of the strongly correlated regime to a CPU treatment of its environment, and if possible, self-consistently coupling it. And then a shout out to Avijit for the development of a very elegant classical coupled cluster-based embedding approach that consistently, actually self-consistently, couples a high-level treatment of a active quantum region to a lower-level treatment of an environment. And that invites Avijit's reach goal for the next year, which is to attempt to generalize this to couple to a suitable quantum solver, and if possible, using an economized cluster ansatz such as UCJ. Anyway, I will thank the people in my group and in Birgitta's group who I've interacted with. So Unpil, James, Hang, Nicolay, Wendy, Avijit as well, and also external collab, Lynn. Nishad Maskara was a very bright visiting student who taught me something about quantum simulators, analog quantum devices, and we had fun with that. Funding from NSF, DAO, and DOE as well. Thank you for your attention.
All right, I guess we'll have questions in the panel. So let's, yeah. We should grab some.